Hi YouTube, welcome to another video on my channel 3D printers and a whiteboard. This video will be the first video in a series about input shaper. Today we will be looking at resonancy graphs generated by Klipper and how to interpret them. We will be having a look at typical graphs, how a well-built printer looks like, and what we can learn about our printers and how to improve them on the graphs. There will be a bunch of additional videos in the future about this topic, which will be more about the technical details and implementation. Today, however, we only focus on the necessary parts on which are necessary to operate our printers, less on the technical details behind it. As you may have noticed, this video is marked as contains paid advertisement. This is due to the fact that we launched a web shop for 3D printer related things, about which I will talk quickly at the end of the video, where we will also be having a small giveaway. So let's get started. Okay, I would like to start at the point where we have generated our graphs. How to generate those graphs. There are additional sources in the internet. I won't do another video on that because there are, I think Nero did one, Teaching Tech did one, and a few others did. And there's also, of course, the documentation by Klipper how to generate those. With Retos, it's really easy. There's even a macro with a button to generate it. So no need that I go into this much further. So now we have generated those graphs, and the question is, what can this graph actually tell us? And that's something I want to have a look at. The first thing, it of course tells us which settings we will later want to use for our input shaper. So this is something we can get input shaper settings we can see on these graphs. How we do that we will learn later. The next thing is if we can see the absolute bell tension, if it's okay, and that's not the case. We don't know if from those graphs if the bell tension is too high or too low. Of course, if you go in really extreme measures like really too low or really too high, we often see it in this graphs, but there's no telling from the graph alone. Relative bell tension on something like a core XY system, if the A and B belts are of this, close enough in tension, that we can see easily on those graphs. And those are things which are really easy to see. Now, the interesting part is, can we see issues in our printer? And the answer is always yes and no at the same time. We can often see that the graph shows some issues with the printer. It's really hard to decide from the graphs what is the exact issue, but things which have influence on the graphs are binding of the rails, for example. Loose bolts you usually see. Over-dampening is mostly easy to see, or it's the loose belt. Over-dampening and really loose belts look basically the same. Issues with the wire loom, like if it's shaking too much and introducing vibrations, we can see that as well. And if the printer has design issues, like if the peaks are not looking good, we can see that as well. Okay, before we go back to the graphs, I want to talk a little bit about resonances in a printer and how they are measured during the resonance measurement of Klipper. So first of all, let's construct a very simple axis, which would be similar to maybe the x-axis of a V-minion. This is a motor here. This is the idler. Then we have a belt running completely around and to some kind of print head. And now if we rotate the motor in, let's say, this direction, we move the print head in this direction. And when we do the measurement thing, we do nothing else than shaking the printer along a defined axis and measuring how the printhead actually moves with an acceleration sensor here. This acceleration sensor compares the actual movement with the one we would expect from this movement of the motor, and therefore is able to see at which frequencies our printer resonates. So let's look at the printer design and how it would resonate. So this is a very simple printer design, which is a separated axis and no coupling between the axes. And we can think of two different kinds of oscillators. One is a linear oscillator, which just means, which is usually the simplest one, is a spring with a mass attached. And this is a simple oscillator. We give it some energy by just expanding it, and then it will start going up and down in a specific frequency. This is the simplest linear oscillator. Linear means that the counterforce to pulling on it is linear to the displacement. And that is what we basically assume within the printer. We assume a bunch of those. And now what is really interesting, they can be coupled or not coupled, which basically means if we have two or more of those kind of oscillators within the printer, they can either like react to a specific frequency by their own, which is a good case because then we just get a peak in the frequency profile, or they can do some nasty things like when they are influencing each other and they get into weird modes, and that's something we don't want to have. So now looking at a perfect printer design, this one here would be perfectly stiff, this one would be perfectly stiff. When we're using aluminum extrusions, those extrusions themselves have a resonance frequency, but this is basically defined by the speed of sound waves within the material, and this is so fast that the resonance frequencies are in a spectrum we don't care about. Now this is a perfect printer axis. Now what will cause resonances all the time, so we always have one, is the belt itself, and we can assume the belt being a spring for the most part, which means when we expand it by a millimeter due to force, it will have a force x to the center, and if we expand it by 2 millimeters, it will be 2 times this force. So for a printer designed like this, which is a Cartesian printer, we have ideally one resonance frequency per axis, which is defined by the length of the belt and the weight which is attached to it. Name the printhead or the print bed on a Cartesian. Now let's think of a Core XY printer. We'll draw the gantry basically of a V-Core 3 from viewing from the top. So this one is X, this one is the Y direction. We have our printhead here, and we have 2 belts. One belt is going like that. And the other is just like that. That would be a typical Core XY. And the printer itself will now have 2 resonance frequencies. And why is this the case? Because the belt, of course, is, when we look at the belt itself, it's a spring all the time, and the same spring. But for movement in X direction, we have different mass than for the movement in Y direction. This is because in X we only move this printhead, and if we move in Y direction, we move the printhead plus an extrusion here. And we have a different damping factor because one time we have 1 linear rail dampening and the second time we have 2 linear rails dampening. From this we can already deduct how a perfect resonance profile would look of our printers, like a Cartesian or a Core XY. So before we now go to have a look at the shaper graphs themselves, I want to talk a little bit about input shaper itself. So now we know how the resonances are measured on the printer with the acceleration sensor. But what actually happens when we apply an input shaper is not that we are countering those frequencies, what is often mistaken for. That's also possible in a control loop, but that's not done in Klipper. What input shaper does is basically avoiding those frequencies. So let's assume we want to print a shape like that. And when we are going with our acceleration and speed, along that to that, that to that, that to that. If that is exactly within our the time we need here, if that is 1/2f, for example, so f is the resonance frequency, you would be all over the place because the printhead would shake all the time in this direction, and then we would have like this shape on those walls. So what does our printer do? It avoids doing this movement in this time frame, and instead it does something like that. So we basically just don't do this exact shape. And this is something to keep in mind for later, because we can see the smoothing does not only depend on the input shaper settings itself, but also on the printed geometry. And I will talk about that later in a little bit more, not in a lot of detail. But that's basically all you need to know. And the input shaper just tries to avoid specific frequencies we measured before. So now I'd like to have a look at the input shaper graph itself. And this is basically two graphs in one. We have the measured spectral frequency over the frequency, but we also have something which is a graphical representation of the input shaper. This here is our x-axis again. This is the printhead. We have the motor. We shake along that direction. And now let's have a look what we can see here. So here we can see those solid lines are for this side of the graph, which is the power spectral density. I'm not going into detail what that actually means. This will be a single video in the future when I go into input shaper by itself and how this power spectral density is calculated and stuff like that. For now, you can only, it's enough to know that this is just a representation of the resonance frequency, so how the response of the system basically to probing those frequencies. Hey, this is future me helping out my past me in the explanation, because maybe it wasn't clear enough what is shown actually. The printhead is probed for all different frequencies during the measurement, and we look at the reaction, and the more it reacts, the closer it is to the resonance frequency. And this is what we can see here. The higher the peak, the more it reacts to the specific frequency. So what we want to have in the end when we are printing is a basically as flat as possible curve. Also, if your graph looks like the one shown here, you can basically immediately stop with the video. If you're not interested in the details, this is how the graph should look like, and if it's looking like that, your printer is doing fine in a specific way. Now, we can see that we have a single peak here, a really small peak here. This small peak, I can just tell that directly. If we ignore that really, really small one, on most printers there's something like that, but it's not really important. And on most printers means on almost all printer designs as well, even on, I don't know, if you look at Voron, Redwick, Annex, or something like an Ender, you will always find this peak in one way or another. So we have one combined resonance. And if we now look at the sensor, which is attached here, we have here our acceleration sensor. The sensor itself has something written on it, which is something like XZ, for example. And those directions written on the sensor are those which we can see here. These are not necessarily the same axis you have on your printer. If we would attach it like I drew here, you can see that the x-axis of the printer is the same direction as the acceleration sensor, and then this x would actually be resonating in x. So that would make sense, but and you can always set your config in a way that even if this is different, it like x gets mapped on z or something like that, so it's always right, but it doesn't have to be, and it's not really important. But if we look at the shape, we can here see the total sum of those three axes. We can see this axis by themselves, and we can see in this case that it's almost only the x-axis causing this. So the overall sum is basically almost the same than the x-axis by itself. When we look at z, for example, this is basically that line here. So there's no movement in this direction. We can measure from going in this direction, which is a good thing, I guess. The same is for y. It's really low here, a peak. This small peak on y, this is a measurement of a core xy, will always be there because there's a small coupling between x and y. As you can imagine, if we look back at what I drew here, when I'm moving in this direction, the belts also go into this direction. There will be a small amount of movement in this direction as well, although they are synchronized in a way so they are almost canceling each other out, the motors. In this way, it's not exactly happening. Okay, so we have our results, and then we have something else, which is the representation of the shaper. It's called shaper vibration reduction ratio. And what you can see is
basically what it means is that where the graph is low for this specific shaper, in this case ZV, where the graph is low, it is applied the most time. So here it will compensate for this measurement the most. Then you can see this is done for all types, and then the algorithm tries to find a specific the right frequency for those specific shapers and then draws them inside here. So if you're not happy with the results the algorithm got, you could also just know, okay, this is the general shape of a ZV, or maybe take a different one like a 2-hump AI, which is the red one. You can see here we have really low, this is the area where it's really low, and we can already see that I think it would be better, instead of doing it like this, to do it like this. You could fit it in a way that it kills this and this frequency. So yeah, you can already see that the algorithm is not working perfectly well, although it does cancel out the biggest peak, so it's not completely off, but probably a little bit better to the left. And that's something you can do, but for 2-hump it's quite hard to know what this means. Like 100 Hertz is basically the frequency between those 2 points. So that's maximum, at the maximum where the maximum compensation happens, and then we have one here and one here. And something like this happens earlier on again, but in frequencies above, let's say 100 Hertz, we don't really do a lot of things anymore because they don't matter a lot to printing. What we're now going to do is to have a really brief theoretical look at how input shaper graphs should look like if they are on an ideal printer. This one is in Core XY printer, and we are going to have a look at our graphs. As I told you before, a perfect printer always has a perfectly stiff gantry, and the resonances of the gantry itself don't matter, only the resonances of a belt. So if we are going to have our X measurements, so we are doing this shaking, we will only have on the X-axis a resonance along the belt path, which will be low, and then we have a peak, and then it will go down again. That's the resonance of the belt. Then we will be having a look at Y, which is shaking it in this direction. And now it gets interesting. It will also have a single peak, but for Y we have 2 different things happening in comparison to X. We have more dampening because we damp on both linear rails and not only one, but we also have more mass because we also moved this extrusion and not only the printhead. More mass means that we are having a lower peak.
Again, future me, what I mean by lower peak is, I mean the peak occurs at a lower frequency.
I will call this peak X, and that one peak Y. This one will be on Y. But we also have more dampening, which means this graph peak usually is lower than the X one. So we have something like this. And those are our perfect input shaper graphs. And this is how a perfect printer looks like. And maybe one interesting thing is to look at a movement in this direction, because this direction would be only driven by this motor in the back. So if, as we know on Core XY, a diagonal movement means a singular movement of a single motor and a single belt. So this movement will have both peaks. And on an ideal printer, let's think about, we need the black one is an axis which is called -1, 1. And then we will create the other belt. If it's also perfect in terms of the same tension, the same length as the other printer, it will look identical. So we have both peaks there and at the same height. And this is all we need to know for a perfect printer. Now, what will happen if we have like different issues here? Okay, so I told you earlier that we cannot see absolute belt tension, but we can see relative belt tension. So what would this look like if it's not the same? We have this movement here, which is our 2 peaks of 1, 1. And then we would have something like this, peaks not on the same level. If this is the case, we know that the relative bell tension is not together and that we need to put those two peaks on one and each other. It's easy to see on this setup, but it's also possible to see on X and Y by themselves, because over there it would look like, I'll do it for one of those, let's use Y, it would usually look like something like this. So we have like a major peak and a minor peak like that. If you have something like this either means that something else is resonating here. This could be anything like a loose bolt most of the times, or the table you're sitting on. But if it's really close to each other, there's a good chance that this is just a bell tension. Of course, if you measure something like this on a V-minion, this won't be bell tension differences. We're only talking about core XY in this case. So let's have a look at binding. Binding is not that easy, because for measuring the frequencies, we only do a really small movement. And those small movements don't always trigger the binding in a way. Sometimes it's only on big movements, but if you can see it in here, it would just create something like this. And usually with really low amplitudes, so we have something like E3 or 1E2 even only on this axis, which is really low, and we get something weird looking. This mostly means that we are like going and stopping, and it's basically random compared to our frequency we are testing, so the graph looks rather random as well. Okay, let's have a look at loose bolt, and we are still looking at a single axis. Loose bolts usually means something like this, a second peak, and it doesn't go to 0 in between. That's really typical for loose bolts. It can be something else as well. It's not like you see that and you know it's a loose bolt, it's just there's a good chance it's a loose bolt. Now, how does overdampening look? Overdampening is a really interesting thing, because mostly if we are overdampening, we are dampening the y-axis more. So we get most of the time something like, there are two indicators. Indicator one is, as we said before, the y-axis has a lower peak than the x-axis. If this is not the case and it's the opposite, like this peak is higher than this peak, which would look like that, this is a clear indicator that we have a dampening problem, in this case on X. And the other indicator for Y dampening problems is usually something like a really low amplitude here, and something like wide and low. That would be an indicator for dampening issues on Y. So what are wire loom issues? Wire loom issues are when your wire loom is vibrating in a weird way, and that's one of those cases. I talked earlier about linear oscillators in the sum of it, and the wire loom usually does not work as a separate linear oscillator, but really by its own, and so it's like going crazy and it interferes with the other resonance frequency. And if we are having a look for X, it would typically look like that. Sometimes there can even be a second peak, but that's optional. But if the edges are really rough of those peaks, this usually means that there's either the acceleration sensor itself is attached in a way that it shakes there, or it's a wire loom to the acceleration sensor, which means when you're detaching it during printing, it wouldn't even influence your printing, or it is actually the wire loom to your printhead. Then you should change that, because that introduces stress to your system, also in a way that it would cost lifetime simply. And there's one other option where it could look like that. That would be broken idlers can also cause these rough edges. So the last thing we are going to have a look at are printer design issues. And printer design issues would just show that we have more than a single peak for a single axis, so something like that, even after debugging the whole system. If this consists over all printer designs, this is a design issue of the printer. It's not necessarily bad. If you look, for example, at the Prusa i3, this one has two peaks because the frame itself is really weak if you don't do the beer upgrade, but it doesn't really matter for low accelerations, so it's not too bad either. Okay, now that we discussed how those things look in theoretically, we will have a look at a few real plots. This is a plot in direction on the diagonals of a core xy, and you can see here we have one time those fitting amplitudes, and one time they are not fitting each other. And this means that the belt tension on this should be corrected. This is fine. It's only important to have the same frequency, the same amplitude, doesn't matter. I won't go into detail why this happens, that we have those different amplitudes. This will be a future topic for another video. So this is one plot where we can see multiple issues actually. Issue number one is that we have those rough edges here. And this is actually due to the wire loom. This one was measured on a V-minion. On the x-axis, this V-minion had some real issues. You can see it in different things. For example, the vibrations which are left after the applied input shaper are really high. The shape is just too wide and too edgy. So we have the wire loom issue. We also have a loose bolt, which causes this second peak here. So those are basically two separate issues, and this just results in input shaper not being able to compensate for that. So this is also an interesting case. We have an x-axis with two peaks, and actually ZV has a lot more acceleration than MZV, where the Klipper tells you it's fine. And the case here is basically that this peak is the one by the belt, and this one is a peak caused by a wobbly table. And this wobbly table will destroy everything. If those differences are really, really high between those different input shapers, that's always an indicator that something is going wrong, like almost 40,000 to 10,000, that's too much of a difference. And funny enough, while it tells you that those two input shapers will result in no ringing, it still happens. It's just not working out. It's too wobbly. So this is another response graph from a eCore 3500, and it actually has a small issue. We can see here we have our peak here, and we have the small side peak, and the small side peaks sometimes don't matter, and you can see that it actually thinks it doesn't matter. But this is a loose bolt in this case, and for big movements on Y it will have more impact than you can see on this measurements graph. So this, if you get something like this, just have a look after applying input shaper. MZV is something to check if everything is okay on a good printer. If you apply it and still got ringing and such a side peak, it's usually an indicator for a loose bolt. Now we will also have a look at this graph to decide for which kind of shaper. As we can always see, the ZV shaper has a really narrow area and also only one peak it can really eat. And Klipper documentation basically tells you to most of the times use MZV. I think if we have this, looking at this one here, if this one is, everything is flat and we don't have the side peak here, the ZV shaper would be enough actually. And you just have to have a look how good it is. It gives you an indication with vibrations left. It's always just a weak indicator, but it is an indicator. One thing to always have a look at are those recommended accelerations at the end. If they don't decrease in this direction, this is a clear indicator something is going on, which you don't want. Here it actually recommends to use MZV, and this recommended shaper is used for the plotted graph, like after shaper, this one. Here, the blue one. That's what it recommends. So the last thing we are going to have a look at are recommended accelerations. And this is something which is quite controversial, but in my opinion, it is not a good way to follow those rules. Like if you are printing and it recommends you to stay below 4,400 millimeters per second square, and you just set this as a limit. You have to look at what you are printing. If we are, for example, looking at the benchmark itself, the Benchy will be looking really nice at 10K as well. But the text at the backside, where there's a lot of detail, a lot of small movements, this one will smooth out. So input shaper tries to avoid your these movements, and therefore basically dampens them out on your shape instead of your movement. It also dampens them out on your shape. But if we are looking at, for example, we are running our print farm, and we are mostly printing big parts with less details, like parts for printers, for example. This part will be looking fine even at much higher accelerations, because the frequency of the movement changes here is much slower than the peaks where we are going to, and so those peaks are not actually part of our movement, and therefore it doesn't really change something. But if we have like an imprint, like a text or something here, which has a really fine structure, those structures will get eaten by the algorithm if the movement is in this frequency range. So this is something to keep in mind. Those recommended accelerations are only a ballpark, and for really detailed prints you want to be lower, and for most prints you can get much higher than the recommended frequencies. Thank you for watching the video. Today we learned how to read the input shaper graphs and how to identify issues on them. As I said at the beginning, we've got an announcement. We started our webshop Sirit Printing. Sirit Printing is a webshop to printer-related things. Currently we are selling APS parts for EVA, vCore 3 and vMinion. As some of you know, we are running a print farm and we have overcapacities these days, so we are creating batches of printed parts. Every time we sell something containing EVA, 10% of what you pay will be forwarded to Pavel and his project for future changes for new hot ends that can be supported, or different fan options, just so Pavel can continue his good work. As I said at the beginning, we also have a giveaway. This giveaway will be a complete set of EVA printed parts with pre-installed heat inserts. And to win this, you have to join our community Discord server and look for the channel giveaways. Thank you for your attention, and